Hello, this is Dr. Hawkins, and today I want to continue and hopefully conclude our discussion on the DC biasing of a bipolar junction transistor. Here is on the left is the circuit. We looked at this circuit last time without the voltage divider attached, just the collector and emitter parts of the circuit. And we determined something that we call a load line. We found the two endpoints, which is a saturation current when VCE is 0, and the cutoff voltage when the, and then we drew a diagonal line that went through those 2 points and said that's, with that choice of VCC, RC, and RE, that was all the possible points that we could operate in. And then by choosing our base voltage through this voltage divider, we're going to narrow that down to a single point we call the Q point or quiescent point. And we, as we stated before, we want that to be roughly halfway in the middle of that load line, so I have room on both sides. If I put an AC signal in, there's room for the amplified AC signal to move back and forth without getting chopped off by one of those endpoints. And just to refresh that just a little bit, well, before I go to the next page, I've listed out the steps here after we find that load line that we go through to find all the other voltages and currents in the circuit. We've got 3 currents, and I'm really talking about the transistor currents. I'm really not that worried about the current through R1 and R2, but I'm talking about IC and IE and IB, and then we've got pin to ground voltages, VB, VC, VE, and then we've got pin to pin voltages, VBE and VCE. Now there is also a VCB I didn't list here because normally we're not really very concerned with that voltage. As long as VCC is bigger than the base voltage, then we're not really that worried about it. But we'll go ahead and add that one on and find it also as we go through this. I also have these equations or steps listed out on the voltage divider bias summary sheet that you can view online or download and print out, whatever you want to do with it, so you don't have to come back and look at this video every time you want to see those steps. And they are listed out in the book also. Now, just as a reminder, last time, here's my circuit again. I want to behave the way I want it to. There we go. There's my circuit again. And to find the load line, I'm not going to draw the picture this time because it takes a while to draw. You can go back and look at the other video, or you can look in the book. It shows it. But we found the cutoff voltage. Let's do it first. That is VCE cutoff. And that's just simply the supply voltage. Because if I set, that's the voltage across the transistor VCE when IC is 0. If IC is 0, that means the current through RC and RE is 0, and Ohm's law says their voltage drops have to be 0. And so Kirchhoff's voltage law says all the supply voltage has to drop across the transistor, VCE. It's acting like an open switch. If I had a switch in a series resistor circuit, when I open the switch, the current goes to 0, the resistor voltages all have to be 0, and that means all the supply voltage has to drop across the open switch. So this is the same thing. That's my cutoff point. That's one end of my load line. The other end of my load line, let me go ahead and write this first. That's when IC is 0. The other point on my load line is when VCE is 0. This is the top left of my load line, the one I've already, the cutoff voltage, the bottom right. When VCE is 0, we get a saturation current, which is at the top left of the load line. Get A out of that center letter. Now, if VCE is 0, that means all my supply voltage has to drop across the two resistors. So the current is going to be the supply voltage divided by the two resistors, RC plus RE, and I'm not going to write the numbers out because we did it in the previous video, but it's 15 supply voltage, 15 divided by 6 plus 1.5. 6 plus 1.5 is 7.5 K, and dividing that into 15 volts will give me 2 milliamps. So that's my saturation current. That's the top left end of my load line. And by choosing a base voltage now, which I believe I've done correctly, we'll find out in a minute. I want my actual operating point to be about halfway in the middle of my load line. So I want a VCE approximately half the supply voltage, which would be 7.5 volts, and I want an IC to be about half the saturation current, or approximately 1 milliamp. Don't have to be exact, but close. We want it close. So this is my goal. Quiescent point. VCE is half of the 15 volt supply. And IC is half of the saturation current. Or 1 milliamp. So let's go through the steps I showed on the previous page. And again, this is on a summary sheet that you can view online or download and print out, whatever you want to do with, but you don't have to come back to the video every time you want to see those steps. And you will have some homework problems on this I'm about to assign as well. Let me pull the circuit back out again. All right, the first step is to find the base voltage. And we're going to use that voltage divider formula that we looked at in the last video. And that's my supply voltage times the bottom resistor of my voltage divider, R2. Is actually what we're finding here is the voltage drop across R2. And that will give us the base voltage. That's over R1 plus R2. Or 15 volts times, it will be a time, so I can get it all in there. There we go. 4.4K over 25.6K plus 4.4K. And when I run the numbers on that, I get 2.4 volts. Now, of course, that puts the voltage right here at the base, right there. And so, since I do have more than 7/10 of a volt there at the base, that tells me that the VBE junction is forward biased, and that also is going to give me VBE. This would be step 2, I guess. VBE equals 7/10 of a volt. And we can also get from that VE is VB minus VBE. .4 equals 1 point. Okay, I made a slight error. This should be 2.2 volts. I knew something was off. 2.2 minus 0.7 will give me 1.5 volts. All right, from that, we can get the emitter current. We know the voltage drop across the emitter resistor. So that's VE over RE. I believe this is step 3. Yeah. Let's go ahead and number it. That's 1.5 volts over 1.5 k ohms. Will give me 1 milliamp. Now, the emitter current is exactly the collector current plus the base current. Remember, we defined base and collector currents as going into the transistor, and emitter current is coming out. And you can do a Kirchhoff's current law here on the whole transistor. What goes in has to equal what comes out. So IE equals IC plus IB. However, since IC is at least 100 times bigger, if we're talking beta equal 100 anyway, that's approximately equal to the collector current. I ran out of room there. Hang on. Okay, so since collector current's 100 times IB, it's a whole lot bigger than the base current, so it's approximately equal to the emitter current. So now that we know the collector current, and it did turn out to be, if you notice, what we wanted it to be about half of the saturation current, and it came out almost exactly half. But proceeding over there, from there we can find the voltage drop across the collector resistor, because we know the current flowing through the collector resistor is the collector current. So the VRC is going to be ICRC, Ohm's law, or 1 milliamp times 6 k ohms. That'll give me 6 volts. From that, we can find VC. We can do a Kirchhoff's voltage law here. We know VC is the voltage drop from there to ground, right? Here's my voltage drop across the resistor. So those two have to add up to equal the supply voltage by Kirchhoff's voltage law. So if I take the supply voltage and subtract the resistor voltage, that will give me the collector voltage. So 15 volts, 6 volts, gives me 9 volts. And we can find the VCE. We define that on a voltage convention as being VC minus VE. Again, that's a Kirchhoff's voltage law thing, actually, but we've already defined it that way. Anytime I have two subscripts that are different on a voltage like this, that's a point-to-point voltage. It's the difference between the 2 point-to-ground voltages with the same subscript. So that's 9 volts. VE was 1.5, and that gives me 7.5 volts. And again, that's exactly half of the cutoff voltage, like we wanted, just like our current was half of the saturation current, just like we wanted. I've left off some numbers here. RC was 4. This will be 5. These are the step numbers again. This is 6. 7, we can find I left off base current on the list of steps too. So let's put it in right here, make it number 7. Let's see. That will give us 10 microamps. And then finally, we can do a VCB. Again, this is something we're generally not interested in, other than as long as we can just look at it and see that the collector voltage supply is bigger than the base voltage, then we know that VCB is going to be reverse biased. But we can go ahead and figure it here. And also it should be the same as the voltage drop across R1 for that matter. And there you have it. There's all the voltages and currents in and out of and around that transistor. And there's a step-by-step procedure. Now notice we haven't done anything really fancy here. We've done Ohm's law. We've done Kirchhoff's voltage and current law. And then we've basically just done add, subtract, multiply, and divide. We hadn't done any calculus or differential equations or anything like that. It's all stuff you supposedly already know. It's just applying it in a new way in these cases with some new theory. It's supposed to be a micro there, didn't show up very well. So I'm going to assign you 2 of these as homework problems. That'll be a separate homework sheet that you can view online or print out or whatever you want to do. If you have access to a printer, I suggest that you print it out and work the problems on the sheet. And to turn it in, again, you can either scan it if you have access to a scanner, or you can just take a picture of it with your phone. Either way, email it to me by the deadline, and I don't have the deadline written down where I can see it offhand, but it'll be attached to the homework sheet. So that'll keep you busy for just a little while. But all you got to do is just follow these steps. And again, I've got a summary sheet of the steps that you can also view online or print out, whatever you want to do with it. And as always, if you have any questions, just shoot me an email and I will answer you as quickly as possible. Hope you're having a safe quarantine and everybody's doing well. So until next time.